Hi, this is the sixth video in Unit 5, and this video is going to talk about electron configurations. Electron configurations are going to describe the orbitals that are occupied by electrons. The orbitals are going to be given a principal quantum number. Remember that number n that started with 1 and then it went to 2, 3, 4, 5, and 6 and so forth, along with the sublevel letter. So we're going to have that S, the P, the D, and the F. And then we're going to have a superscript number, which will be the number of electrons in that orbital. Now we're going to be following a principle called the Aufbau principle, and what this states is that when we're filling in the electrons in an atom, we're going to start with the lowest possible energy level first. When that energy level is filled, then we move up to the next higher energy level and so forth. It's also known as the building up principle. We're also going to follow the Pauli exclusion principle, which states that no two electrons in an atom will have the same set of 4 quantum numbers. And what this really means is that an atomic orbital can only hold a maximum of 2 electrons, and those 2 electrons will have opposite spins because their spin quantum number will either be plus 1/2 or minus 1/2. What we need to know is what are the energy of these orbitals? Who is the lowest energy? Then what comes next? We're going to be working with this a lot in class, but for right now we're going to start with a very simple energy of orbital diagram. So what you see here is that the lowest energy orbital is the 1s orbital. It's the one in blue. And that box represents the orbital, and it can contain a maximum of 2 electrons. And we'll represent the electrons with arrows, and the opposite spins will be with 1 arrow going up and 1 arrow going down. After 1s comes the 2s orbital, and then come the 2p orbitals. And notice there are 3 of those orbitals. So the 2p, there are 3 orbitals. We're going to come back to this diagram. All right, so let's just get started and write the electron configuration for atoms. All right, well, we're going to start with hydrogen. And remember, hydrogen only has 1 electron. So where are we going to put that electron? Well, let's look back at our energy diagram. We're going to use the Aufbau principle. We are going to put that electron in the lowest possible energy level. And if we were doing an orbital diagram, we would put that electron indicated by this arrow in the 1s orbital. But the electron configuration for hydrogen is 1s, and then we're going to say 1. So it's 1s, 1. There's 1 electron in the 1s orbital. Well, let's go to helium. It has 2 electrons. So here we go. We're going to go to the lowest energy. Aufbau says to do that. Pauli exclusion principle says within that 1s orbital, we can have 2 electrons, but they have to have opposite spins. So there we go. That would be the orbital diagram for helium. The electron configuration for helium would be 1s, 2. And this superscript 2 says that there are 2 electrons in that 1s orbital. Okay, now what are we going to do? Lithium has 3 electrons, and our 1s orbital is now full. So we're going to have to go to the next available orbital, the one of lowest energy. So let's put 3 electrons in, and those will be for the lithium electron configuration. So here we go. For lithium, we're going to put 2 electrons in the 1s, and then we're going to go up to the 2s orbital. That's the orbital diagram. The electron configuration would be 1s2, and then in our 2s orbital, we just have 1 electron. Okay, well, let's skip ahead to nitrogen. And nitrogen is going to have 7 electrons. Okay, I had to think there for a minute. Okay, so let's go back to nitrogen. Okay, so with 7 electrons, we're going to put in the 1s. We're going to fill it up, and our 2s is going to be filled up. And then here we are in the 2p's. So right now we only have 4 electrons in, but we're going to add 3 more. The question becomes, how should we add them? Should we add 2 in this orbital, then move on to the next? Well, what we're finding out, what we need to do is we need to add 1 electron to each. Okay, And so for the orbital diagram for nitrogen, it looks like this. 2 electrons in 1s, 2 electrons in 2s, and then 1 electron in each of the p orbitals. These p orbitals are all the same energy. These 2 p orbitals, it has a fancy word. It's called degenerate. But we're going to put 1 in each of the orbitals before we go back and pair them up. And the 1 electron that we put in each orbital, they all have to have the same spin or the same orientation. Okay, so what would that electron configuration for nitrogen look like? It would look like 1s2, 2s2, and then in our electron configuration, we don't really designate that those electrons are in 3 different p orbitals. We just say that there were 3 electrons in those 2 p orbitals. Okay, so that would be the electron configuration for nitrogen. Well, let's check. The superscript is the number of electrons. 3 plus 2 plus 2 equals 7. And that is the number of electrons for a nitrogen atom. All right, well, what we just did by putting 1 electron in each p orbital before we pair them up, that's called Hund's rule. So when there are orbitals that have the same energy, like those 2 p's had, you're going to place 1 electron in each orbital, and then you'll go back and pair them up. That's called Hund's rule. Okay, well, what about higher energy orbitals? Okay, the lowest energy is 1s, followed by 2s, and then there are our 3 2p orbitals. And after that, we have a 3s orbital. We have the 3p orbitals. But then what comes next? Well, surprisingly, the next lowest energy orbital is the 4s orbital. Notice it's below the 3d. So after 3p, we're going to fill in the 4s orbital. When that 4s orbital is filled, then we fill in the 3d. And after, oh, look at that, there are 5 of those d orbitals. After the d's are filled, then we'll move up to the 4p. And again, we're going to practice this order of filling orbitals a lot in class as we practice electron configurations. Well, let's go ahead and write the electron configurations for these following atoms. So we're going to do aluminum, sulfur, potassium, and iron. Okay, so for, let's see, aluminum has 13 electrons. So let's go back and write the electron configuration. We need to put in 13 electrons. So the 1s is going to be filled, the 2s is going to be filled, the 2p is going to be filled. Notice I'm putting 1 electron in each before I pair them up. I'm following the rule set by Hund's rule. I'm following the alphabet order, lowest to highest energy. Okay, so now I need to fill in that 3s. And let's see, I've got 2, 4, 6, 8, 10, 12, and there's 1 more electron in the 3p orbital. All right, so the electron configuration for aluminum would be 1s2, 2s2, 2p6, 3s2, 3p1. All right, let's go on to sulfur. All right, if you look at your periodic table, sulfur is atomic number 16. And so an atom of sulfur would have 16 electrons. All right, so 16, here we go. Alphabet order, 1s2, 2s2, Pauli's rule, putting opposite spins. I'm going to follow Hund's rule, 2p, and actually we're going to have to fill that up, so it's 2p6, 3s2, 3p. Now we have right now 12 electrons. There's 13, 14, 15, and now for our 16th electron, we're going to go back and start pairing them up in that 3p. Okay, so our electron configuration for sulfur would be 1s2, 2s2, 2p6, 3s2, 3p, and how many electrons are in that 3p? Well, there's 2 there. They're kind of a mess. 2, 3, 4. 3p4. And we should have all of our numbers should add up to 16. Our superscripts, 6, 12, 14, 16. That's the electron configuration for sulfur. This diagram here where I'm filling in these boxes or these orbitals, that's called an orbital diagram. This 1s2, 2s2, this whole thing there, that is called an electron configuration. Okay, now let's do potassium. Potassium has 19 electrons. All right, so we got some work to do. Okay, so the 1s2 is filled, the 2s2 is filled, the 2p is going to be filled, but just from habit, I'm used to using Hund's rule. I'm going to put one in each orbital and then go back and pair them up. The 3s is filled, the 3p is filled. Now, right now, how many electrons do I have? 2, 4, 6, 8, 10, 12, 14, 16, 18, and then where should I put that 19th electron? Who's lower in energy, the 4s or the 3d? And the answer is the 4s is lower in energy, so that's where that electron is going to go, in that 4s electron. That's the orbital diagram. We had to fill up the 4s before the 3d because it's lower in energy, and Alf-Bal says we have to do that. All right, here we go. Electron configuration for potassium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s, and there's only one electron in there. Electron configuration for potassium. Okay, iron. Iron has an atomic number of 26. So it has 26 electrons. We've got some work to do, guys. Let's write the electron configuration. Okay, 1s2, the 2s will be filled, the 2p. Notice I'm going from lowest energy to highest energy, putting 2 electrons into every orbital with lowest spin, and I'm just going to keep going until I get to 26. All right, I've got my 3p filled in. Next comes the 4s. And now the next energy after 4s is 3d. So right now I have a total of 20 electrons, and iron has 26 electrons. So I'm going to fill in the 3ds. It's the next lowest energy orbitals. I'm going to follow Hund's rule, put one into each of those 5d orbitals. That's 25, and there's number 26. So that's the orbital diagram for iron, and its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 comes next, and then 3d6. This is the old way that people used to write electron configurations. You write them in the order that you fill them, but actually there's a new way now where you start out the same, but you would keep all these principal quantum numbers of 3 together. So you do 3p6, 3d6, and then put the 4s2 at the end. Either way is fine. It's just a matter of the order that you write the end orbitals, and so it really doesn't matter to me, but you can see it either way. Okay, electron configurations. We're going to practice that a lot. The hardest thing is just knowing the order to fill them in, and I'm going to give you a lot of helpful tips on that as well in class. All right, so we're done with that. What we have been writing are electron configurations of atoms in their ground state. And the ground state is the lowest possible energy for the atom. And so you've noticed that every electron, it occupies the lowest possible energy orbital available, and then once that's filled, then we move to the next higher energy. So that's what we've done so far. We've written the ground state electron configurations. And that's what you should write unless you know otherwise. But if they're not in the ground state, you need to be able to recognize an electron configuration of an atom in the excited state. And that's just where an electron has been promoted to a higher energy level. So you're going to see something where a lower energy orbital's not filled completely, but then higher energy orbitals are. So these electrons have left their ground state. Maybe they've been heated or some electricity has been added to them and they've jumped to a higher energy orbital. We have no way of knowing at this level where those electrons jump to, so all you're responsible for is recognizing an electron configuration for an atom in the excited state. Well, this is part 1 to electron configurations. You'll watch the other part tomorrow. We're going to learn a shorthand for electron configurations, and then we're going to learn how to write electron configurations for ions as well. All right, we'll see you tomorrow. Bye.